In this session, we will discuss about inverse Laplace transform by using partial fraction method. So consider L inverse of s plus 1 divided by s square plus 2s. So in order to apply partial fraction method, consider the function f of s. F of s equal to s plus 1 divided by s square plus 2s. Now, the denominator function s square plus 2s can be written as s into s plus 2. And here, these two are linear factors. So, we can write s plus 1 divided by s into s plus 2 in the form a divided by s plus b divided by s plus 2. Now to find values of a and b, take the LCM of denominator. So we can write s plus 1 divided by s into s plus 2 equal to a into s plus 2 plus b into s divided by s into s plus 2. Therefore, we can equate the numerators s plus 1 equal to a into s plus 2 plus bs. That is, to find values of a and b, now equate like terms on both sides of this equation. So here, the constant term is 1 in LHS. So consider constant term on both sides of the equation. So we get 1 equal to, on RHS constant term, so 2a and here 0. So from this we get a equal to 1 by 2. So that if you consider coefficient of s, we get 1 equal to a plus b, and we know that a equal to 1 by 2, substitute in this equation, so that implies 1 equal to 1 by 2 plus b. So we get value of b equal to 1 by 2. Now, substitute values of a and b in this equation. So we get L inverse of s plus 1 divided by s into s plus 2 equal to 1 by 2 divided by s plus 1 by 2 by s plus 2. Or if you take the inverse transform of 1 by s, 1 by 2 is constant, so take it outside the operator, is 1 by 2 into L inverse of 1 by s plus 1 by s plus 2. Now we know that inverse transform of 1 by s, that is 1, and the inverse transform of 1 by s plus 2 is e raised to minus 2t. So this is 1 by 2 into L inverse of 1 by s plus L inverse of 1 by s plus 2. So that is equal to 1 by 2 into 1 plus inverse transform of 1 by s plus 2 is e raised to minus 2t. Therefore, L inverse of s plus 1 by s square plus 2s is equal to 1 by 2 into 1 minus e raised to minus 2t. So in order to verify this, you can take Laplace transform of RHS. So we get this function f of s. Now consider another example. Find L inverse of 1 by s square minus 5s plus 6. So take f of s equal to 1 by s square minus 5s plus 6. To factorize this denominator, I can write denominator in the form s minus 3 into s minus 2. Now apply partial fraction method. So this can be written as a divided by s minus 3 plus b by s minus 2. Now to get values of a and b, equate like terms. So 1 equal to s minus 2 into a plus b into s minus 3. Therefore, if you equate constant term, we get 1 equal to minus 2a minus 3b. Put it as equation number 1. And if you equate coefficient of s, we get 0 equal to, here coefficient is a plus b, or that implies b equal to minus a. Now if you substitute b equal to minus a in equation 1, we get 1 implies that 1 equal to minus 2a minus 3 into minus a, or that implies 1 equal to minus 2a plus 3a, or it is equal to a. So a equal to 1, which implies that a equal to 1 and b equal to minus 1. Therefore, L inverse of 1 by s square minus 5 plus 6 is L inverse of this a by s minus 3 plus b by s minus 2, and we get values of a and b. So substitute values of a and b in this equation. L inverse of 1 by L inverse of 1 by a equal to 1, so it is 1 by s minus 3 plus b equal to minus 1, so minus 1 by s minus 2. Or by linearity property of inverse transform, can write this as L inverse of 1 by s minus 3 minus L inverse of 1 by s minus 2. Therefore, L inverse of 1 by s minus 3 e raised to 3t minus L inverse of 1 by s minus 2 e raised to 2t. So we get inverse transform of function 1 by s square minus 5s plus 6. Now consider another example. Find L inverse of 5 divided by s minus 1 into s square plus 2s plus 5. So consider f of s. F of s equal to 5s plus 3 by s minus 1 into s square plus 2s plus 5. Here the denominator factors are s minus 1 and second degree polynomial s square plus 2s plus 5. So consider the corresponding terms in the partial fraction. F of s equal to 5s plus 3 by s minus 1 into s square plus 2s plus 5. So that is equal to a divided by s minus 1 plus, corresponding to the second degree polynomial, the term in numerator is bs plus c divided by s square plus 2s plus 5. Now to get values of a, b and c, make the denominator equal on both LHS and RHS. So 5s plus 3 by s minus 1 into s square plus 2s plus 5 equal to a into s square plus 2s plus 5 plus bs plus c into s minus 1 whole divided by s minus 1 into s square plus 2s plus 5. Now since the denominators are equal in both LHS and RHS, this implies that can equate numerators 5s plus 3 equal to a into s square plus 2s plus 5 plus bs plus c into s minus 1. Now equate like terms on both sides of this equation. So this implies first equate constant terms. So here constant is 3 equal to constant is 5. So 5a, and here a term b s square and b, so minus bs plus cs, so minus c. So this is equation number 1. And if you equate coefficient of s, here coefficient of s, LHS 5, look at RHS, coefficient of s 2a, and here it is bs into minus 1, so minus b, plus c into s, so plus c. It's equation number 2. Now equate coefficient of s square. So LHS there is no coefficient for s square, 0, plus equal to a RHS a plus b s square, so b. It's equation number 3. But from 3 we get 3 implies that b equal to minus a. Substitute b equal to minus a in equation 1 and 2 and solve. So for b equal to minus a, equation 1 implies that 3 equal to 5a minus c. With respect to this substitution, b equal to minus a, 2 implies 5 equal to 2a minus b, b is minus a, so 2a plus c, or 2 become 5 equal to 3a plus c. Now add these two equations, so we get 5 plus 3 equal to 8, and c minus c 0 equal to 8a, so that we get a equal to 1 or b equal to minus 1 because b is minus a, and since a equal to 1, equation implies, first equation implies that 3 equal to 5 into 1 minus c, so we get c equal to 2. Therefore, a equal to 1, b equal to minus 1, and c equal to 2. Now substitute these values in this equation, we get f of s equal to a by a is 1 by s minus 1 plus b is minus 1, so minus s plus c is 2 divided by s square plus 2s plus 5. Now look at the second term. So we know that inverse transform of 1 by s minus 1 is e raised to t, but for second term we need to apply square completion here in denominator. So look at the coefficient of s, that is 2. So we can write this denominator in the form s plus 1 the whole square plus 4. Therefore rewrite denominator in second term, so minus. So here minus s plus 2, so plus minus s plus 2 divided by s plus 1 the whole square plus s plus 1 the whole square is s square plus 2s plus 1, so plus 4, 5, so we get constant 5 here. And since s plus 1 is present here in the denominator, we need to get s plus 1 numerator also in the place of s, so rewrite s as, so take minus n outside, this becomes s minus 2 divided by s plus 1 the whole square plus 2 square, write 4s2 square, So this is 1 by s minus 1 minus, now replace s by s plus 1, and constant is minus 2, so subtract 3, s plus 1 minus 3 divided by s plus 1 the whole square plus 2 square. Therefore, L inverse of f of s equal to L inverse of 1 by s minus 1, L inverse of RHS, and apply linearity property of inverse. You can write this as 1 by s minus 1 minus L inverse of s plus 1 divided by s plus 1 the whole square plus 2 square, again minus into minus is plus, 3 into L inverse of 1 by s plus 1 the whole square plus 2 square, or it is equal to inverse transform of 1 by s minus 1 is e raised to t minus, here if you take exponential outside, this becomes e raised to minus t into L inverse of s by s square plus 2 square plus 3 into numerator is constant and b equal to 2, so 3 into e raised to minus t into L inverse of, so multiply and divide by 2, so divide by 2, 2 by s square plus 2 square. Again, if you consider inverse transform of s by s square plus 2 square, that is cos 2t, so I can write this as e raised to t minus e raised to minus t into cos 2t plus 3 by 2 times e raised to minus t into sin 2t. Therefore, inverse Laplace transform of the given function f of s is e raised to t minus e raised to minus t into cos 2t plus 3 by 2 into e raised to minus t into sin 2t. Now, we will discuss about solution of differential equation by applying Laplace transform method. For that, we need to consider the formula solution of differential equation by using Laplace transform. So here, if you consider Laplace transform of derivative of a function, let that function be f of x. What is Laplace transform of first derivative f dash? So it is defined as s into Laplace transform of f minus f of 0, the value of the function at 0. If you replace f dash by f double dash, what is Laplace transform of second derivative f double dash? Then it is s square times Laplace transform of f minus s into f of 0 minus f dash of 0. So f dash value at f dash at x equal to 0. If you generalize this, you will get f triple dash. Then it is s cube into Laplace transform of f minus s square into f of 0 minus s into f dash 0 minus f double dash 0. So it will continue like this. So for nth derivative, it is s raised to n times Laplace transform of f minus s raised to n minus 1 f of 0. So in general, fn, nth derivative, is s raised to n into Laplace transform of f minus s raised to n minus 1 into f of 0, s raised to n minus 2, f dash 0, etc. fn minus 1, 0. So this is the general formula for finding Laplace transform of nth derivative of a function. So we can apply this method, this formula, to find the solution of a differential equation, ordinary differential equation. For example, consider the equation, solve the equation y double dash minus y equal to t with respect to initial conditions y of 0 equal to 1 and y dash 0 equal to 1. So these two are the initial condition. Now, in order to apply the Laplace transform method, consider this formula. So consider the equation y double dash minus y equal to t. Solution. For that, consider the given differential equation. Now take Laplace transform on both sides of this equation. Laplace transform of y double dash minus y equal to Laplace transform of t. And we know that it is linear, so it is Laplace transform of y double dash minus Laplace transform of y equal to Laplace transform of t. Therefore, if you apply this formula, Laplace transform of second derivative of a function y double dash, this becomes a square into, so for Laplace transform of y double dash, it is a square into Laplace transform of y minus s into y of 0 minus y dash 0 minus L of y. So L of y is L of y itself. If you want, you can take L of y as, if you assume that L of y equal to say y bar, then we can replace L of y with this y bar. And what is L of t? RHS L of t, Laplace transform of t is 1 by s square. Therefore, in terms of y bar, you can write this equation s square y bar minus s into, and here initial conditions are given, so y of 0 is 1, substitute it here into 1 minus y dash 0 is 1 minus 1 equal to 1 by s square. So s square into L of y minus s into y of 0 minus y dash 0, so minus L of y equal to 1 by s square. So s square y bar minus s, so minus 1, so minus this y bar, L of y is y bar equal to 1 by s square. Or if you collect terms containing y bar, you can write this as y bar into s square minus 1 minus s minus 1 equal to 1 by s square, or y bar into s square minus 1 equal to s plus 1 plus 1 by s square. Therefore, y bar equal to, you can write y bar as y bar equal to s plus 1 divided by s square minus 1 plus 1 by s square into s square minus 1. Now simplify this s square minus 1 can be written as s plus 1 into s minus 1 plus 1 by s square into s square minus 1. That is s plus 1 by s plus 1 into s minus 1, this is 1 by s minus 1 plus 1 by s square into s square minus 1. Now, again if you apply the partial fraction method, so we get the inverse transform of y bar, which is the required solution. Therefore, L inverse of y bar equal to y of t, and that is equal to L inverse of 1 by s minus 1 plus L inverse of 1 by s square into s square minus 1. So just find its inverse by applying partial fraction method. So we get solution e raised to t plus sin ht minus t. Obviously, inverse transform of 1 by s minus 1, that is e raised to t, and apply partial fraction here. So we get this solution. Another example, solve the differential equation y double dash plus y dash plus 9y equal to 0. It is given that y of 0 equal to 0.16 and y dash 0 equal to 0. Solution. So consider a given differential equation y double dash plus y dash plus 9y equal to 0. Now take Laplace transform on both sides of the equation. So it implies that L of y double dash plus y dash plus 9y equal to L of 0. And by linearity property, you can write this as L of y double dash plus L of y dash plus L of 9y equal to 0, because L of 0 is 0. Now consider the formula for y double dash, L of y double dash, s square into Laplace transform of y, let it be y bar, minus s into y of 0 minus y dash of 0, plus for L of y dash, again apply the formula s into y bar minus y of 0, plus 9 constant, so take it outside the operator, 9 times L of y is y bar equal to 0. Now substitute the initial conditions given. So y of 0 is 0.16 and y dash 0 is 0. So this equation implies that s square y bar minus s into 0.16 minus y dash 0 0 plus s into y bar minus y of 0 0.16 equal to 0 plus 9y bar equal to 0. So y of 0 is 0.16 plus 9y bar equal to 0. So this is that s square y bar minus 0.16x plus sy bar minus 0.16 plus 9y bar equal to 0. Or if you take collect terms containing y bar, so y bar times s square plus s plus 9 minus 0.16 s minus 0.16 equal to 0. Or this implies that y bar into s square plus s plus 9 equal to 0.16 s plus 0.16. So I can write this as 0.16 into s plus 1. Therefore, y bar equal to 0.16 into s plus 1 divided by s square plus s plus 9. Hence, the required solution is y of t, which is L inverse of y bar, is obtained by taking the inverse transform of RHS, that is 0.16 into s plus 1 divided by s square plus s plus 9. Now, here can apply the square computation procedure. So, coefficient of s is 1. I can write this as 0.16 into, so y bar equal to 0.16 into s plus 1 by s square plus s plus 9, so that we get y of t equal to L inverse of y bar is L inverse of 0.16 into s plus 1 divided by s square plus s plus 9. So, if I consider coefficient of s, its coefficient is 1, I can write this denominator in the form s plus 1 by 2 the whole square, and constant is 9, so 1 by 2 whole square, it becomes s square plus s plus 1 by 4 plus 35 by 4, so 36 divided by 4 is 9. I can write the denominator s square plus s plus 9 in the form s plus 1 by 2 whole square plus 35 by 4. Therefore, this is equal to 0.16 into L inverse of, if you consider denominator, here the term s plus 1 by 2 is present, so correspondingly we have the term in numerator also. So I can split this as s plus 1 by 2 divided by s plus 1 by 2 whole square plus 35 by 4. 35 by 4 can be written as root of 35 by 4 whole square plus, so this is L inverse of, so plus 0.16 into L inverse of, second term is 1 by 2 divided by s plus 1 by 2 whole square plus root of 35 by 4 the whole square. Now, we know that since that term is s plus 1 by 2, can take exponential function outside. The corresponding exponential function is e raised to minus 1 by 2t into L inverse of s by s square plus root of 35 by 2 the whole square plus 0.16 into e raised to minus 1 by 2t into L inverse of 1 by 2 is constant, so you can take outside the operator, so 0.16 by 2, 1 by s square plus root of 35 by 2 whole square, or it is equal to 0.16 into e raised to minus t by 2 inverse transform of s by s square plus s square form. So that is cos root of 35 by 2t plus 0.08 into e raised to minus t by 2 into, here numerator is constant, so it is 1 by b, b is root of 35 by 2 into sine root of 35 by 2t. So this is the solution of a differential equation y double dash plus y dash plus 9y equal to 0 with respect to this initial condition. Thank you. Y bar into s square plus s plus 9 equal to 0.16 s plus 0.16. So I can write this as 0.16 into s plus 1. Therefore, y bar equal to 0.16 into s plus 1 divided by s square plus s plus 9. Hence, the required solution is y of t, which is L inverse of y bar, is obtained by taking the inverse transform of RHS, that is 0.16 into s plus 1 divided by s square plus s plus 9. Now, here can apply the square computation procedure. So, coefficient of s is 1. I can write this as 0.16 into L inverse of s plus 1 divided by s plus 1 the whole square plus s square plus s plus 1. So what is remaining? 8. The constant is 9. So s square plus s plus 1 plus 8. Therefore, this is 0.16 into, here I can write 8 as root of 8 square. So this becomes 0.16 into e raised to minus t, because s plus 1 is present in both numerator and denominator, L inverse of 1 by or s by s square plus root of 8 square. So it is of the form s by s square plus s square. So its inverse transform is cos at. So this is 0.16 into e raised to minus t into cos a equal to root of 8 t. This is the required solution of the given differential equation. Thank you.